Well, hello everyone. My name is Chiranjeev, and in this video series, you will be learning the structural design patterns. So, structural design patterns are basically responsible for building simple and efficient class hierarchies and relationships between different classes. So, there are quite a few design patterns in this category, and we will be discussing adapter, bridge, composite, decorator, facade, flyweight, and proxy. We'll go through all these structural design patterns one by one, explaining the problem it is trying to solve and the UML diagram. And we'll also go through a coding example which will explain a real-time scenario where we can apply this design pattern. So starting off with the adapter pattern, let's take a look at what is adapter pattern, what is the problem it's trying to solve. We'll also take a UML diagram of adapter pattern as discussed, and we'll take a look at the coding example. So let's get started. Well, adapter is a structural design pattern that allows objects with incompatible interfaces to collaborate. Now, what does this mean? What does this incompatible interface to collaborate mean? This is the main essence of this adapter design pattern. So what adapter pattern basically allows it allows some interfaces which are not incompatible, which we want to reuse. Adapter By using adapter pattern, we can reuse those interfaces without writing extra code. So the way this design pattern works is it converts the interface of a class into another interface which client is expecting. It also lets classes work together that couldn't work otherwise because of the incompatibility of the interface. Let's quickly try to visualize the problem this adapter pattern is trying to solve. Let's imagine a scenario where you have an application in which the client program is talking to a file system, and the way the interface behaves, it is exposes two methods: to read from the file system and to write to the file system. So let's imagine a scenario where you want to support one more file system which also behaves in a similar way, but the interface it is providing is not equal or compatible with the interface the client code is already using. So let's look at the UML diagram first, and then we will try to see what is going on behind the scenes. So this is the UML diagram for the adapter pattern. So as you see, you have a client which is always targeting a object which is of type target, and there is a request method in that object which client is accessing. So let's say you have one more uh, class which has also a similar kind of behavior but not the interface. So that means that the interface it is providing is different from the interface the client is already expecting, in this case, which is request. And the interface which our expected class is providing is a specific request. So you see there is a kind of similarity where this client code can be reused to work with the near adaptee object which we have in this problem. So the way to solve this problem is to add an adapter which implements the interface which client is already targeting to, and have a reference to an adaptee which this adapter will adapt to. So what this adapter will do is take the client request and convert it to the request which this adaptee supports. So let's take our file system example. Let's say your client is writing to a NTFS system which is providing read from the system and write to the system as two interfaces. So this client only knows two things: read from the system and write to the system, and it does not know anything what is going behind the scenes. Let's say you are injecting a NTFS file system which is implementing those methods. Now you want to extend the functionality and you want to add support for, let's say, ext file system, which is basically used in Linux. But the problem here is that those file system does not have these methods. Let's say those file system have completely different sets of interfaces for reading and writing to those systems. So what we can do there is inject an adapter and which will implement the interface the client code is using and give and have a reference to the newer adaptee class, in this case our Linux file system, and we will just delegate the call from the client to the newer specific method of that particular file system. So the way to implement this, we'll just quickly take a look in Java and we'll try to code this. So let's take a look at the coding example. Here I have created a very small example to demonstrate the working of adapter pattern. So what we're doing in this example is we are simulating some birds. So here our client class, this is our client class, which is referencing a target interface. So here, in our case, the target interface is a bird interface. And the only thing this bird interface does is to make sound. So any class which implements this bird interface will have to give a special behavior for this make sound method. So I have created one dummy bird, which is called duck. As you can see, I'll remove these borders. So the make sound method is implemented by this duck class. And let's go to our client class quickly. And as you can see, we are instantiating this duck and we are depending on the interface to actually have the functionality of this client. We're depending on the make sound method. Now, let's say your requirements change and now you want to also include plastic birds or plastic toys, whatever makes sound in your simulator. So you happily go and create a class because plastic toy birds, let's say for some time, don't have this make sound method there in the interface, and instead what they do is squeak. So whenever you squeeze some plastic toys, this is the sound they make. So every plastic toy, bird, or whatever can have their own implementation of their sound. So I have created one more class which is called Winnie the Penguin, which implements the plastic toy bird, and the implementation is it is squeaking. So whenever this squeak method is called, it squeaks. But how can we use this plastic toy bird interface with our bird interface? Because since our client code is strictly dependent on our bird interface, it is tightly coupled to the method it is calling. So to solve this problem, what we saw in the UML diagram is we need to create an adapter class which will implement the target class and have a reference to the adaptee. Let's quickly go in our code. So to demonstrate this, I have already created a bird adapter. And since we are targeting the bird interface, we are implementing the bird. Let me remove that. Okay, so we have implemented the bird interface. And after implementing the bird interface, what we need to do is we need to override the make sound method in the bird interface. So that's what we did. Now the second point says we need to have a reference to an adaptee. So in this case, our adaptee is toy bird. Our toy bird is adapting to our bird interface. So we have a reference to our adaptee. And to instantiate this adaptee, I am taking a reference in the constructor and setting it here. So let's quickly go to our client code and see how we can implement this. So in our client code, when we instantiate the bird object, what we'll do now is again create a bird, which will be our toy bird. And to instantiate with the adapter pattern, what we'll do is we'll create an instantiate of the instance of the bird adapter. And here we will pass a plastic toy bird. So the implementation of our plastic toy bird is inside this Winnie the Penguin class. So we'll pass the Winnie the Penguin class and close the line. Now, if you actually do toy bird dot make sound and actually run this, you'll see that squeaking output is there, which means that whatever was there in the Winnie the Penguin, which implemented the plastic toy bird interface, which was nowhere equal or equivalent to our bird interface, now we can use that. So this is how we implement the adapter pattern. It's a structural design pattern which lets you uh, use those interfaces which don't have compatible exposed methods. So we saw how our client is using the target method and how we can actually create one more adapter using our target and have a reference to our adaptee and actually delegate the call from the target to the adaptee and get the output. So thank you guys for watching my video, and in the next video we'll discuss the bridge pattern. So see you in the next one. Hi everyone, my name is Chiranjeevi, and in this video we will continue our discussion on structural design patterns, and in this video we will take a look at bridge pattern. So following the pattern in the previous videos, we will discuss what is bridge pattern. We will take a look at the definition. Then we will take a look at the problem it is trying to solve, the UML diagram, and a code example. So let's quickly dive into the definition for the bridge pattern. So this is the definition for the bridge pattern. It's a structural design pattern that decouples an abstraction from its implementation so that two of them can vary independently. Well, comparing with the other design patterns, this bridge pattern specifically was more complex to understand for people who are starting out in the design patterns. And if you look at the definition, there are quite a few points which you should note what this pattern is trying to do. So what it says here is bridge pattern decouples an abstraction from its implementation so that two of them can vary independently. So here what we need to identify is what's an abstraction and what is the implementation of the abstraction. So after identifying what kind of abstraction and what kind of implementation are there in the code base and what are we actually trying to decouple, then only we can understand what this bridge pattern's intent is, what is it is actually trying to do. So to understand this pattern, first we will take a look at some of the examples, then we'll take a look at UML diagram of the bridge pattern and exactly try to find where actually the bridge lies in the UML diagram and in the bridge pattern. So let's take a look at some of the examples here. Okay, so this is the first example we will discuss as a problem which actually gives us a way towards, or which actually tries to bend us towards the bridge pattern. So these kind of scenarios which I'll discuss in this video are the actual building blocks and actually the reasons why you actually need a bridge pattern. So let's discuss this example. In this example, what we have is a thread scheduler, which is an abstract thread scheduler which has some actually extensions which are preemptive thread scheduler and a time sliced thread scheduler. So now let's say each of the thread scheduler again has a platform specific behavior. So for example, Unix systems have their own implementation of the preemptive thread scheduler, and the Windows system have their own implementation of preemptive thread scheduler. Similarly, on the other hand, let's say for time sliced thread scheduler also we have a Unix based implementation and a Windows based implementation. So up to here it seems pretty good. This design seems pretty good. But what if, let's say we want to add one more platform support to this hierarchy? What will the code base look like? So this will look like this one. So let's say we are adding a support for Java Virtual Machine platform, and you can see that we are adding one more extension for the preemptive thread scheduler and a time sliced thread scheduler in the UML diagram. As you can see, this is starting to look pretty ugly because every time you need to add a support for a newer platform, you need to extend and give behaviors for all the thread schedulers there are actually in the hierarchy. So let's say that you have not two thread schedulers in the hierarchy, but you have 20 thread schedulers, but you have only two platforms and you want to add one more platform to the hierarchy. So what you'll have to do is to provide behavior for all the 20 thread schedulers which you already support. And this will be kind of a coding nightmare which will you never want to get into. So here in this UML diagram, as we discussed in the definition, what we are trying to do is to abstract the behavior for the thread scheduler. But what we see here is that actually the implementation for the thread scheduler is actually dependent on the platform itself, which can vary according. So what bridge design pattern says, when you actually encounter these kind of issues, what you actually do is you have to decouple an abstraction, which in case is our thread scheduler. And we have to decouple the abstraction from its implementation. So we can see that our implementation for the thread scheduler is platform wise. All right. So we'll see in the next UML diagram how we can avoid this. So this is the UML diagram for the bridge design pattern. And what this UML diagram and bridge design pattern suggest is that the client will only talk to the abstraction layer, and the internal implementation which you want to vary will act as a interface where you can inject the behavior based on the implementation. So let's take a look at this example in a more deep way so that you understand the actual essence of this pattern. Okay, so if we compare this design pattern with the adapter design pattern, so adapter design pattern actually gives you a way to make things work after they are designed. But you can apply bridge pattern to the problem to make them work before they are actually implemented. Also, if you look at some of these structural design pattern like strategy pattern and bridge pattern and state pattern, all they have a common or similar solution structure where you can actually imagine the UML diagram like a handle slash body idiom. What this handle slash body idiom means, like you have an abstraction which behaves like a body for your solution, which will have all the logic on how to operate on the actual implementation, and this body will be actually talking to the client, but internally you have a handle to flip the behavior in the runtime so that you can actually have any kind of possible permutation of your combined logic. So here in our case, to implement the thread scheduler, what we need to do is we need to abstract the thread scheduler by providing an abstraction which the client will be talking to, and have a interface for the platform itself which will provide all the functional and behavioral implementation for different kinds of platform. And what we will be doing is injecting that interface in the abstraction at runtime to get different behaviors for every kind of possible combination. So this is actually pretty good. It gives you a great amount of control on how you want to actually make your inheritance hierarchy look, and it also is very manageable because every time you want to add need to add a platform or a new abstraction, all you need to do is to only extend the abstraction or implement a new implementation. So every time you feel like you have an orthogonal dimension of dependencies which can exist independently and kind of have a combination between the two orthogonal hierarchy, you should go for the bridge pattern. And the way you can identify is looking at this diagram. When you see like you have abstraction which have two kinds of behaviors, and for each behavior you have certain kind of repeated behavior across the entire inheritance hierarchy. At that point of time you can actually know that here I have two orthogonal hierarchies which I can vary independently from each other. So in scenarios like this you can actually have bridge pattern applied to it. One more example people gave to explain this bridge pattern is like you have a shape which is an abstraction, and then you have an implementation level layer which is of color. So every shape is can be of red, blue, or green color, and they explain you like if you want to add a yellow color shape to the inheritance hierarchy, it will be a complete disaster. So you can also actually discuss this here. So this thread scheduler can behave like the shape, and this primitive and time slot search schedulers can actually behave like like square and rectangle. And this platform level implementation can be termed as red color square, green color square, or blue color square. Similarly here also, let's say you want to add one more shape to the hierarchy. Let's say you want to add a triangle to it, and then you want to add a red triangle and a blue triangle and a green triangle. So the solution to these kind of orthogonal hierarchy problems, which have a very involved combination of this abstraction and implementation combination, what you can do is to separate out these hierarchies. So what you will have is a shape abstraction, and every kind of shape will actually extend this abstraction and give their own behavior. And on the other hand, you can actually inject an implementation which will be of color, and every color implementation can actually go and implement their own behavior in their own way. And all this abstraction will do is talk to the client class, but internally it will have a reference to the implementation which will be injected at runtime to actually flip the behavior of this abstraction as required. So this is a very nice design pattern, and I like it a lot because it gives you so much flexibility you have in the code using inheritance. So we will quickly go and try to code this shape example in Java and take a look at how this saves us from coding a hell lot of classes. So I have created a very small example which will demonstrate the usage of bridge pattern in Java. So let's look at our code and let's try to map it to the UML diagram we saw for the bridge pattern. So the first part is the client part. So I have created a client class which is named client, obviously, and this is actually where we are implementing and testing our code for the bridge pattern. So for the abstraction, what we are trying to make something abstract here, and that abstraction here is our shape class. And in the shape class, what we are doing is we are providing a shape type and an area. So the area method is actually abstract, and the subclasses will actually compute the area. Along with that, we have also a property called color, which is our implementation, which can vary from the abstraction. So if we go inside this color, this is actually an interface which provides its own behavior of filling the color. So I have created two colors, which are the red color and the green color, which simply return the color of the given object. So let's say green color returns solid green color and the red color returns solid red color. So we will be able to swap the colors from the shape abstraction independently. Now let's say how we are extending this shape abstraction into multiple different subclasses. So I have a square created out of shape which has its own side length and a way to compute the area. And similarly we have a rectangle class which have its own length and breadth, and it has its own implementation to compute the area. In the constructor of square and shape and rectangle, I'm taking the color type for the shape and actually passing it to the base abstraction, which is our shape class. And in the shape class, I have provided one method to actually set the color independently of what kind of shape we have. So if you can pass actually a color, and the color handle will actually start pointing to the new color you point to. So we'll quickly go to our client class and see how this actually lets us switch the behavior of the implementation from the abstraction at runtime. So let's go to our client class. Let me remove all this code I have already written here. So let's go ahead and quickly create a shape which is of type square, and we will pass a length of the side to it and a color type. So let's say we are passing a red color. Now to display actually the shape, what I have done is provided a method to paint the shape, which will actually display what color of the shape is. So let's quickly run this code and see what is the output of the program. So as you can see, we are seeing painting square with solid red color. So let's go ahead and create a rectangle, which is called rectangle, and we will pass length 6 and width 4 and a color type of green color. And let's say we want to print the uh, what color is of the rectangle. So let's run this code again, and you can see how easy it is to create and vary the implementations for the abstraction. Now let's say after some time you got bored of this red color square and now you want to change it. So what we will do now is we will uh, slightly refactor our code, and what I'll do is just copy this code here. We'll create a reference for red and green color. Let's also rename this to red color. Now instead of creating a new object every time, what you can do is reuse this red color and reuse this green color which we have already created. Since the function inside this red and green color is purely it's a pure function which is not dependent or has no state, so the only job of this function inside the red color is to paint the shape. So let's say you want to have a square which was initially of red color, but now you want to change it to a green color square. So what you can quickly do is square dot set color, and here you can actually pass the green color. And now when you do the square dot paint shape, the behavior of the class is actually changed at runtime without any code changes to the existing code. So as you saw in the UML diagram where we discussed that every time you wanted a different combination, you needed to add it across the hierarchies for the abstractions. But here, after implementing the bridge pattern, what we can do is add implementation here and inject it at runtime, and it will still behave the same. So that's what we are doing here. We are adding one more green color implementation and we are injecting it inside here. Let's say, so today we don't have any yellow color here. So what we can do is just quickly go and create a yellow color which will implement this color interface, and quickly come here and actually inject the yellow color, and without any changes your square will start accepting yellow color because it's still of type color and it only depends on the paint shape and the fill color method. So your code will completely accept the any new colors what you add as implementation of the color class, and also your older color class will be able to work with the newer abstraction. Let's say you add a triangle to the inheritance hierarchy, so it will be taking that into account. So this is how the bridge pattern works. I hope I have made you understood how it behaves. If you have any questions, you can ask it in the comments, and in the next video we will be discussing the composite structural pattern. So I'll see you in the next one. Thank you guys.
Well, hello everyone, my name is Chiranjeevi and welcome to my structural design pattern video tutorial series part 3. And in this video we will basically be covering the composite design pattern. We'll take a look at the definition, the UML diagram, the problem it is trying to solve, along with a code example. So let's quickly dive into what is a composite design pattern. So according to the definition, it's a structural design pattern which we know already, and it lets you compose objects in a tree structure and allow clients to work with these objects as if these were individual objects. So, well, it's a little tricky to imagine the composition of objects as trees and managing all these client and allowing the client to work with all these objects as if they were individual objects. So let me just describe a similar example. So as you can see in the first image, we are displaying some black boxes uh, along with the heading of the video. So in composite design patterns, so let's say you might have a scenario where you want to use some of the objects which are embedded inside the same object, and are of same types and support a same type of operation. So let's say you have a gift box. All right, so a gift box can have a gift as well as another gift box which is put inside that gift box. So as you can see here, we have some boxes. So these boxes can have separate products, or this box can also contain a smaller box or a set of small box which in turn contain a product or a set of smaller box. So you see, right, there is a kind of similarity in the behavior, the, there is a kind of similarity in the structure, and the way you want to implement this in code. Let's say you want to unwrap this box, right? So unwrapping of the box will not depend whether the box is a parent box or a child box. The unwrap will behave in a similar way. But let's say you are unwrapping a parent, and let's say you find a leaf and there are two other boxes. So what you want to do is to delegate the call of unwrap to the other two boxes which are present in the interface, and so on and so on and so on, until you open all the boxes inside this. This seems a little bit tricky because as soon as you start coding it, you will have to deal with the container boxes and the containing boxes in a very different way. To solve this problem, what people suggested in Gang of Four is like you have a separate common interface which will expose all the operations you want to perform on the box, basically, be it a leaf node or be it a composite. So by here, leaf mean that it's not a box, it's actually the content of the box and you want to perform some operation on that. And you can also add the composite itself, the box, which contains, again, may contain some boxes inside or some products. So that's what we want to do. So we will expose all the functionalities in a component interface, and all this leaf and composites will derive from this component interface. And this composite will have a list of components which will create a tree kind of structure where each composite has a list of components, and each composite in the list of that component has again a list of components, and so on and so on and so on. So this actually creates a tree kind of structure. And when you actually invoke the operation on a composite, it's actually quite interesting to see how this composite will iterate over all the composites and invoke their operation, which is already defined here. And this will recursively call every other operation in all the components present inside the composite. So yeah, this seems a little bit tricky at once, but once we see a coding example, it will be very clear to you. So let's go into the coding example now. Alright guys, so I have already created a coding example. So I will walk you through each of the pieces one by one, and we will map our coding example with this UML diagram, and we will create a small demo on how this works. Okay, so the interface which we will be defining in this example, we will be mapping it to the component interface we have seen here in the UML diagram, which has all the operations which we want to handle in a separate way. So let's go to the code, and here you see I have named the interface surprise box. So whatever is inheriting this interface, that will also be a type of surprise box, and it will have all the operations I will define in this interface. So to start with, let's define one method which we'll call unwrap, and every surprise box you at least need to unwrap it, right? And the way you unwrap a surprise box will not change, and you will always call unwrap to unwrap the surprise box. The other is a leaf one, and let's go to our gift class, and you see here, right, gift class implements the surprise box. So let's give it some behaviors. So let's first give our gift a name. So we'll say private string name. Let's name it to gift name. Now let's also initialize this gift with a name provided in the constructor, and let's set this name to gift name. We will also implement the unwrap method which we got when we extended this sorry implemented this interface called surprise box. So let's go ahead and do that. So we'll say unwrap, and here let's just say system.out.println unwrapping gift and followed by a gift name. Alright guys, so whenever you unwrap the gift, this will display a message which will say unwrapping this gift and followed by the gift name. So that's it for the leaf class which we saw here. Let's go and let's code our composite class. So in this code example, I have named our composite class as gift surprise box, and this is a surprise box which is actually wrapped in a gift foil, and you can actually unwrap this and it will have certain amount of embedded gifts inside it. So let's have a array list of gifts. So we will say array list of surprise box, and let's name the surprise boxes. Let's also create a constructor for this class, and what we will do in this constructor is initialize this surprise boxes to this new array list. Now let's add some more methods to actually add to this surprise boxes and remove from this surprise boxes. So let's quickly go and define the add method, and what we will do is this will take a surprise box which we call box, and this will add it to the surprise boxes, and we will say add.box. Let's also add a remove method which will do remove from the surprise box, and this will also take an instance from the surprise box, and this will say this dot surprise boxes dot remove the box. Now we are almost done with coding the composite. The only thing which we need to implement is the unwrap method which we get when we extend this implement this surprise box interface. So our interface method is unwrap. So what we will do inside this unwrap is for each of the surprise boxes, so let's say surprise boxes for each, what we will do is we'll call the unwrap of the surprise box. So let's say surprise box dot unwrap. So this is actually a method reference which will pass which will call the unwrap method for each of the surprise box in this array list. This is actually a Java 8 syntax. If you're not familiar with method references, for now just assume that for each object it will call this unwrap method inside the surprise box class. So now we are done with coding our gift surprise box, and let's go to our client demo to actually code the example and see it in action. So we'll go to our client demo class, and let's create some gift boxes. So let's create our first gift surprise box. We'll call this gift box, and let's say gift box. So this initializes the array list inside the box. Now let's add one more gift surprise box which will be the child of this box, and we will say sub gift box. We'll also initialize this gift surprise box. Let's create some cool gifts for our little brothers. We'll say gift is equal to new gift, and let's name this gift a toy car. Also let's create one more gift. We'll say gift 2, and we will say new gift, and we will say toy plane. Yeah, but the way we will pack this is we will have this root gift box which will have a toy car, and this sub gift box which will have a toy plane. Okay, so let's correct this, and we will put this sub gift box into the gift box, and when we call the unwrap of this gift box, all this toys should be unboxed. So let's add. So we'll say gift box dot add. Let's add a gift there, and we'll say sub gift box dot add. Let's add gift 2 there. Now let's add sub gift box to this gift box class. So let's say gift box dot add, and we'll pass our sub gift box. So our composite is built now. Now if we want to unwrap this, what we'll call is the unwrap method on the root gift box, and it will unwrap all the internal gift boxes, whatever is present inside. It will also unbox all the composites and call the unwrap on each of the object inside the composite. So let's say gift box, which is our root gift box. Let's say dot unwrap. Now this should unwrap our toy car and a toy plane. So let's run this code. And as you see, it first called the toy car, then it went inside the sub gift box, then it checked for all the gifts which are present inside the sub gift box, and then it also went ahead and unwrapped those gifts also. So yeah, that's it with the composite design pattern. We saw how to implement this in Java using our coding example. So if you have any queries, you can ask it in the comments. Otherwise, I'll see you in the next one with the decorate pattern. Thank you. Alright everyone, welcome to my structural design pattern video tutorial series part 4, and in this video we will learn the decorator pattern. So let's quickly have a look at the definition first. So what decorator pattern says, it's a structural design pattern, as we all know, but what it lets you do is it lets you attach new behavior to objects by placing them into wrapper objects that contain this behavior. So what does this mean? Let's have a very small example, and this is a UML diagram for the decorator pattern. So what it says is whatever you want to decorate and whatever you want to decorate it with, you inherit or you provide the behaviors for all these two different components in a separate component, and you actually extend that behavior from that component. So it's very similar to the composite pattern where you also wanted to use the objects in a similar way. So in composite design pattern, you wanted to use the containers and the containing object in a similar fashion. Now here you can actually assume this decorator pattern as a special case for composite pattern, and in which every container will have only one containing. So since it's a decorator pattern, we say like every component can be decorated with every other component, and the decorator will contain the component which is to be decorated. So I know it sounds very confusing at first, but let's imagine a scenario where you are programming a application for an ice cream factory and you want to compute costs for different kinds of ice cream. So what you have is a base ice cream class, and let's say you want to sell the ice cream in a cone. So what you will do is inherit from the base ice cream class and create a ice cream with a cone, and then you will add a separate get price method to that. Let's say the ice cream shop changes its policy and also now wants to sell ice creams instead of cones. It also wants to sell ice cream in cups. So let's say now you'll again go and inherit from the base ice cream class and create one more subclass which will provide the behavior for this. Now let's say you want to add some choco chips on the top of these ice creams. Now what you will do is you will create two more classes, one which will have the cone with choco chips base ice cream and one with the cup with choco chips base ice cream. So you see how this small example is exploding into an exponential number of classes when it comes to having all the different combinations of components. All right, so what we can do is instead of having an inheriting from the base ice cream class, what you can do is actually create a interface which will handle both the decoratee and the decorator in a similar fashion. So we will have one component which will have all the operations exposed in one interface, which will expose the behavior, how do you want to handle the decorator, and the decorator will have a reference to a component which can again be another decorator or a concrete component, and it can apply all the same operation on that too. So this will be a little complicated to understand at first, but what we will do is take a very uh, similar example from our Java file IO, and we will see how it works. So we'll basically be creating a reader class which a file reader will be implementing, and the file reader will be our concrete component. Now what we'll do is create separate decorators which will be like encrypted file reader and compressed file reader. We'll create these several decorators, and we'll wrap our file reader class around these decorators, and we'll get completely different behaviors. So we'll be able to create different kinds of combinations for the file reader class using our decorators. Now imagine what we'll have to do if we wanted to create the same functionality using the base inheritance. That will be a very trivial approach, and it will actually explode into a number of subclasses, because then you will create a file reader which has the encryption functionality and the compression functionality. You can create a file reader only, you can create a file reader with a compression functionality, or you can file reader with only a encryption functionality. So these kind of combinations and problems will arise, which you'll have to take care. But with decorator pattern, this uh, problem will be very small, and we'll be able to deal with all the possible number of combinations which can be done, which can be created at runtime. So all you need to do whenever the new combination comes is to add a new decorator to it, and that's it. And you can pass your decorator object, which in case our file reader object, to the decorator, and you can actually have the new behavior wrapped around the file reader object. Also, the decorator pattern is used to add additional responsibility to a class. So we know, like, every single class you code should be have only one responsibility, and according to the single responsibility principle, uh, the class should have only one reason to change. Now let's say you want to use all the same functionality, but you have one extra responsibility which you don't want to keep in that class. But instead of going through the inheritance way, we will favor a way to create a new behavior for the class and give it to a separate class, and we'll not use inheritance, we'll use composition. So let's go and take a look at the coding example, and that will make things more clear. Okay everyone, so in this example we will map our example from the UML diagram, and we will be arriving at this finished product. So we will create a decorator which will decorate our file reader with the compressed file reader and the encrypted file reader. So this encrypted file reader will first decrypt the file, then decompress. The compressed file reader will again decompress the file, and then the file reader will actually read the file from the specified location. So let's delete all this code and let's code it again from scratch by mapping it to the UML diagram. So we will be coding this from scratch. So firstly what we will do is we will go to our reader class and define a method called read, and we will be using this reader class to actually specify the component. So if you go to our code, this reader is actually acting like our component. Now we'll go ahead and create our concrete component on which we want to apply all our decorators. So for this example, our concrete component will be this file reader class. So let's create some private members. So first will be the file path from where we want to read this file. Then we will create a constructor, so public file reader, and then this will give this string parameter which will initialize a path inside this file reader. So we'll say this dot file path equals path. Now we also have to implement the read method since we are implementing the reader interface. So we will say public void read, and in the read method will have our logic to read the file. So for now, let's simply print out system.out.println reading file from the specified path. So we'll say this dot file path. So that's what the read method is doing. It's actually reading the file from the file path, and to dummy the behavior, we are just printing a line from it. So now our concrete component is ready, which supports the following operation, which is our read method. So let's go to our decorator and create some abstract decorator. Then we'll inherit some concrete decorators from the abstract decorator. So let's go to our read decorator, which is already implementing the reader class. So we will go ahead and have a reader which is living inside this read decorator, because we have a reference for the component. So now we will initialize this reader from the constructor. So what we will be doing is we will pass a reader reference to the constructor, and in the body of the constructor we will set the reader to the reader which is passed. Now we don't need to actually implement the read method in the abstract class. What we will do is implement the read method in the consequent concrete decorator classes. So for this read decorator, this is enough. Now we will start coding our concrete decorator. So we will quickly go to our compressed file reader. Now this is actually class which extends the read decorator, which actually implements the component which we want to decorate. So we'll go to our compressed file reader and we say extends read decorator. Now here let's create a constructor for this compressed file reader, which will again take a reader object, and it will just set the it will just pass this reader to our super class. And also, since this is not an abstract class, we need to give definition to our read method, which we implemented from the reader interface. So here we will say system.out.println, and we will say decompressing the file. Okay, so we are saying decompressing the file, and after decompressing, when you are done, just invoke the reader which you have decorated already. So we will say this dot reader dot read. So now what this will do is actually decompress. You will have all your decompression logic here before it. You'll retrieve the decompressed file and then again actually pass that to the read object. So this is how that works. Now we are done with the compressed file reader, and let's quickly go to our encrypted file reader. Here also we will quickly create our constructor, which will take a reader reference. So reader, and we'll say this dot reader is equal to reader. We'll also quickly go and implement the read method. So this will say system.out.println, and we will say decrypting file, and after the decryption is done, what we will say is this dot reader dot read. So what this encrypted file reader will do is it will actually call the reader read method after processing the decryption algorithm. So okay, there is no default constructor available in read decorator. Okay, so we have to call the super. Basically we need to pass this reader object in the super class. Alright, so we are done coding our encrypted file reader. Now we are done with coding all our decorators, concrete component. Let's go to our client demo class and we will actually code this. So let's say you want you just want a file reader. So let's say file reader, and you don't want any decoration on the file reader, you just want the vanilla file reader. So we will say file reader, and let's give it a path of c/test.txt. so now you are actually want you have created a file reader which will read the file from the following location. If you say file reader dot read, what it will actually do is it will read it from the given path. So you see reading file from c colon slash text. Now let's say you want to create a file reader and which will say I want to read a file but it is actually compressed. So let's say you are creating a compressed file reader, and to do that what we need to do is we just need to decorate our file reader with our compressed file reader. So we will say new compressed file reader and we will pass it a file reader. So now let's say you have this file reader which is capable of reading the compressed files, which internally uses a file reader which is actually there. So when you invoke the read method on this file reader, so let's say compressed file reader dot read, it will actually first decompress the file and then read it. So let's run this program and let's see this in action. So yeah, we see decompressing the file and then reading the file from the following location. Let's have some print line statements to actually differentiate the output for different file readers, and we will just print some thing like this. Okay, now we can actually see the difference in the output. So this is the output before the decompressed file reader, and now when we applied this decorator we are actually decompressing the file and reading it again. Let's again actually have this border in the console, and now let's create a file reader which can actually read encrypted files. So we need an encrypted file reader, so we'll say encrypted file reader, and what we'll do is we'll create a new encrypted file reader and pass the file reader which we already have. So let's say now this c test.txt is an encrypted file, so what we want to do is we want to decrypt it first and then read it. So let's call the read method, and then what you'll see is that we are actually decrypting the file and then reading it. So we are adding more responsibilities to this file reader and without creating any extra inheritance hierarchy. Now let's say you want to add one more file reader which will support both encryption and decryption. So let's add one more border like this, and let's say you want to create a reader which is a encrypted compressed file reader. Now what you want to do is you want to create a new encrypted file reader, then you want to pass it a new compressed file reader which will again take a new file reader which will again take a path to some text2.txt file. Okay, so we are passing our file reader to a compressed file reader, and then we are again decorating it with the encrypted file reader. So what this will do is before reading the file it will first decrypt, then it will decompress, and then it will read. So let's create let's see this in action. So encrypted file reader dot read, and here we are. So you can see it's decrypting, decompressing, and then reading. What you can also do is change the order of the decorators, and these order are completely independent. So let's say you want to first decompress, then decrypt, and then read. So what you can actually do is let's copy this code. Let's say compress
compressed encrypted file reader. So now what we want to do is we want to create a compressed encrypted file reader. So see how easy is this to create several combinations of this file reader. You just want to change the order of the decorator. So now we are reading this. Okay, let's add some borders to the console so it's clear for you to see. Let's add this. Now let's run our code. Save, run. So okay, so now you can see it's actually first decompressing the file, then decrypting the file, and then reading it. And I had it's actually decrypting and then decompressing. So the order is completely changed and the behavior is also completely changed. And what you didn't do any class changes, you already had a set of decorators, and you can use this use these decorators to actually decorate this file reader in any possible way you want. So you see, right, there is a file reader setting at the bottom. You decorated the file reader with the encrypted file reader, and then you again decorated it with a compressed file reader. So that's it with the decorator pattern. That's it how we add responsibilities, add multiple responsibilities to existing classes without the use of inheritance. And it's actually a very flexible way to do it. So I hope you have understood what is decorator pattern, and in the next video we will cover the facade pattern. So I'll see you in the next one.
Alright everyone, my name is Chiranjeevi and I am back with one more structural design pattern, which is called the facade design pattern. And to explain this pattern, we will first take a look at the problem it is trying to solve. But yeah, I have put a very nice image of a little castle over here, which will actually represent the meaning of this facade pattern. So let's quickly take a look at the definition, and then we will try to relate it why and how facade pattern works. So facade is a structural design pattern that lets you provide a simplified interface to a complex subsystem of classes, library, or a framework. So let's say you have a system in which you are doing so many things and you have so many state to maintain in the system, and you do not want to expose the internals of the system to the world, but you do want the world to use your system, and at the same time you don't want to expose the internals of your subsystem to the world. So the way you expose your subsystem to the outside world, what you will do is you will expose an interface which will be our facade, and that interface will only support those functions or operations what you want to expose for the subsystem. So this is what the definition is trying to say. Let's say you have a very complex system of classes or a library, but you actually don't want to expose the internals of your library, right? So what you will do is expose an interface which will actually perform the operations for you, which the library will be performing underlying, without exposing the internals for the library. So that's what the facade pattern is for. It's a structural design pattern which lets you provide a simplified interface to a complex system of classes. So we have discussed the problem. Let's jump right over to the UML diagram. So here we have a small subsystem of shapes, and what all the shapes allow is you can actually draw them. So we have an abstract shape class, and we have three extensions for this shape. We have circle, rectangle, and a square, and all of them provide one draw method, which is being overridden in the respective subclass. Now we don't want to expose the internals of this shape subsystem. What we will do is we will create an interface which will actually talk to our shape subsystem, and this interface will expose only those methods which we want to support. So let's say you have one more shape called triangle, but it is still in the testing phase, and you don't want the user of this subsystem to actually be able to create triangles. But the only way to restrict them is to restrict access to the subsystem itself. So here the shape maker, which is acting like a facade, will actually provide only those methods which you want to implement. So since there will be no draw triangle method in your facade, no user using this facade will be able to talk to your subsystem and will able to request you to draw a triangle. And that's it. What you do is you expose a set of methods what you want to support for your subsystem without allowing the client to actually interfere with the internals of the subsystem. So that's it with the UML diagram. Let's actually have a look at the running example. So we will try to map our UML diagram with the code example. Here we have a shape subsystem which represents this abstract class, and it has a draw method which does not return anything, it simply draws. And we have three implementations for this shape, which is circle, rectangle, and a square. And all these circle, rectangle, and square do is override this draw method and provide their respective implementations for the shape. Now let's go to our ShapeMaker class and we'll see how this ShapeMaker is actually letting this main client draw these different kinds of shapes without letting it access the internals of the subsystem. Oh, this is our ShapeMaker facade, and you see it has a reference to all your private shape subsystem classes. It has circle and a rectangle and a square, all which is private to this facade only. When you instantiate this facade will request the creation of all the relevant subsystem objects which you want to deal with. Now we have provided three different methods, which is draw circle, draw rectangle, and draw square, which we have provided over here. And all this is doing is calling the draw method for the respective class. Now let's say your shape system has one more class called triangle, but if you don't provide an implementation or a way to actually create or draw a triangle here, this client will not be able to actually draw the triangle. So whenever you want to use this shape subsystem, you will talk to your shape subsystem using this facade. You will instantiate a facade object and you will ask the facade to do the logic for you. So that's it with the coding example. Since it was a very small example, I preferred it not to actually code it in a live way and actually pre-code it and actually show you the example how it works. So that's the facade pattern. If you have any doubts, you can ask it in the comments. Otherwise, I'll see you in the next one. Welcome back everyone to my structural design pattern series, and in this video we will discuss the proxy design pattern. Let's quickly have a look at the definition and the problem it is trying to solve. So the definition says that it's a structural design pattern that lets you provide a substitute or a placeholder for another object to control access to it. Alright, so the definition is quite simple, but the problem here is, why do you actually need a substitute or a placeholder for another object if you have the object itself? So the reason we need a placeholder object for another object might be, like, let's say the object you are trying to use is very heavy on system resources and it takes a lot of resources to create that particular object. Now let's say you have a lot of places in your code where you are trying to instantiate this object and you are performing some operations on this object, and there's a lot of pre-instantiation phase which you always need to verify whenever you want to use this object. So to always abstract all this pre-instantiation logic and all those pre-steps before instantiating an instance or asking that object to perform an operation for you, what you actually do is create a placeholder object for the object itself. And the interface which this placeholder object provides is the same interface which the original object provides. What this placeholder object does, it's as it can do the validation for you, whether actually the inputs you are giving or you are about to give to the objects are valid or not. And based on that, you could actually reject or continue the behavior. The benefit with this approach is, whenever you are using a proxy, all this pre-instantiation and prerequisite code is not actually scattered in your code base. It sits at one place inside the proxy object. So whenever you want to talk to the actual object, which is a very high consumption and resource taking object, you wrap it in a proxy and then give it to the client. Let's take a look at the UML diagram. So in the UML diagram, the client is actually needing a service interface which has some operation, let's say. Now let's assume that this operation is very expensive to perform, and given invalid inputs, this operation can take a heavy number of resources and actually fail, which is not expected. So what we do is, for this service, we abstract this operation in an interface called service interface, and then we derive two implementations for this interface. One is the service itself, and the other one is the proxy service. So this proxy service will actually have a reference to the actual service it is trying to target, and in the constructor you can actually instantiate this proxy with a service of any type you want. And this proxy, since it is implementing the same interface as the service itself, it will also have those operations in the background. And we can actually have some pre-processing logic before calling the actual service in the proxy. So this is what proxy pattern is trying to do. It is trying to pre-process your inputs before actually calling the actual target service. Let's take a look at the coding example. The coding example I have written is inspired from this UML diagram, so you will find a very direct similarity between the UML diagram and the coding example. Here we have the coding example, so let's go to our service interface. This is a very small interface which has only one operation called the perform operation. So, and there are two implementations for this service interface. One is the service itself and the other one is a proxy. So let's go to the service itself, and I have named it actual service. So let me remove the podders so you will be able to see what's happening here. And in the actual service, what I'm trying to do is actually I'm giving a behavior to this perform operation. I'm giving it a method body. In this body, I'm trying to actually invoke the actual operation. And let's assume that this operation is quite expensive and we don't want to actually just directly go and invoke this operation. We want some prerequisites to be checked. So for the prerequisites class, I have created this service proxy, which actually implements the same service interface and has a reference to the actual service. As you see in the UML diagram, we have a private reference to the actual service, and in the constructor we are initializing the service, and similarly in the constructor we are actually initializing the service. Now in the perform operation method of this proxy object, we are logging some text which is going through proxy, and before actually invoking the actual perform operation, you can do all the pre-processing logic here. So for demo purposes, for the pre-processing logic, what I'm doing here is just printing out some println statements, which is proceed, invocation, data validation, complete. So whenever this client wants a proxy service, we give it a proxy, and this proxy can be decided through a factory pattern, and we have discussed it in the creational design pattern series. So if you have not watched it, you can just go and check it out. So service interface will have a reference to a proxy, and the proxy will perform all the prerequisites which are needed to actually invoke the operation in the actual service. This is the problem it is trying to solve, and we have seen how it is trying to solve the problem. So this is the intent of the proxy design pattern. Let's take a look at the definition again. Proxy is a structural design pattern that lets you provide a substitute or a placeholder for another object to control access to it. Now you know why do you need a substitute, what is a substitute, and how to use it. Okay, thanks guys for watching my video, and I will see you in the next one with a flyweight design pattern. Alright everyone, welcome to my structural design pattern video tutorial series, and in this video we will be discussing the flyweight design pattern. Let's have a look at the definition for this flyweight design pattern. So flyweight is a structural design pattern that lets you fit more objects into the available amount of RAM by sharing common parts of object state among multiple objects, instead of keeping it in each object separately. Okay, so there are so many things going on here, so we will take down this pattern one by one, and let's look at the important pieces of the definition and what this flyweight design pattern is trying to convey. So what it says, it's trying to fit more objects in the available RAM. So it's doing the job of reducing your object size so that more objects could be fit in your RAM. And how it does that is by sharing common parts of object state among multiple objects. So if you have multiple objects which have same states and all these same state is replicated across your multiple objects, that will consume more memory. And since the replicated state can be shared among objects, since this replicated state can actually be shared among all these multiple objects, can actually drastically reduce the memory usage. So that's what it says. Instead of keeping it in each object separately, you keep it apart from every object, and all the other objects will have reference to this unique object. So there are two things in flyweight design pattern. So to understand this problem, actually you need to be familiar with two definitions. The first one is the extrinsic state and the second one is the intrinsic state. So the intrinsic state of an object is that state of object which does not change and can be shared across multiple objects. As we see in the definition here, we are talking about sharing some state for our object, and that state which we will be sharing across objects will be the intrinsic state. And the next state is extrinsic state. The object, the states which make each object unique from each other despite having some common state is called extrinsic object. So those properties which are unique for each object itself is called extrinsic state. Let's look at the UML diagram. We have looked at the problem it is trying to solve. So the UML diagram, we have a context which has both unique state and flyweight state. So this unique state actually can be derived from a flyweight factory which will provide you all the possible unique states your objects can have, and this flyweight factory will actually maintain an internal cache and it will only return you objects from cache whenever requested. If the object is not present in the cache, the factory will actually create it for you and then give it you the object from the cache. And for the extrinsic state, you actually provide the value in the constructor itself, but to get the unique state, you actually ask the factory to do so. So let's quickly have a look at a coding example where we will be designing this pattern from the scratch. And the example I'll be using is an example for the bullets and guns. So the example will be involving some bullets and guns. So let's quickly go and code this example from scratch. I'll be explaining how this works and what is my example. All right, everyone, here we are back with our coding example. So in this example, I have already created some classes to demonstrate this. So the classes we have is a bullet factory class, which will be generating bullets for us and which will also have a cache as specified in the UML diagram. So our bullet factory is our flyweight factory. Then we have a bullet type. Bullet type will actually decide, will be used by the factory to decide what kind of bullet to create at runtime. Then we have our extrinsic state, which is the gun. The gun will have all the extrinsic state and the intrinsic state. So we have this abstract gun class over here, which we will be filling in later. And this shotgun class will be extending this gun class and provide its own extrinsic state to the gun. And finally, we'll use our hunter class to actually execute this program. So first, let's go to our bullet type class and let's decide what type of bullets do we want to have. So the first category, I'll like to have some pistol bullet. I'll name it pistol bullet. Then I would like to have some shotgun bullets, and I'll also like to have some sniper bullet. Let's give our bullet a name. So we'll say private string name, and let's uh, create a default constructor which will take a name for the bullet type. So this will set the name here. Also, we need to call the constructor for each of the instances. So for pistol bullet, we will say MG45 bullet. So this is the name of the bullet. For the shotgun, we will say Koi 84 bullet. And for the sniper, let's say M14 bullet. So we have our bullet type ready, and let's go and actually code our bullet class. So here we are in our bullet class, and let's add some behaviors to it. But remember, when we discussed this UML diagram, we mentioned about extrinsic and intrinsic state, and the most important thing about your intrinsic state or the unique state is it should be immutable. And by immutable, you should not be able to modify the object once it is created, because since this object is shared across multiple objects, this unique state will always be a read-only state. Once created, you cannot touch it anymore or modify it. So I have declared this class as final. Let's go ahead and create some variables. We'll create a variable called bullet size. So we'll say private final string bullet size. Then we will say private final string bullet weight. Let's create a default constructor for this, and we'll say bullet string size comma string weight. Let's initialize these values. So we'll say this dot bullet size is size, and this dot bullet weight is weight. So we are done with coding the constructor here for, and since it's a final class, we are not going to provide any setter methods, but since it's a read-only class, we should provide getters for bullet size and bullet weight too. Get bullet weight. Okay, so we are done coding with this bullet class. Let's go to our bullet factory and code this bullet factory. So we are done with this flyweight object and this unique state. We'll go to our bullet factory and code this factory. So remember, this bullet factory is using a internal cache to actually cache this object. So let's create a cache. So we will create a static map of bullet type and bullet. Let's import this, and we will call this bullet cache. Let's initialize this to new hash map and create some factory methods. So we will say public static bullet get bullet by type, and we'll say bullet type here. And here will be just a switch statement which will return the instances of bullets based on the type. So let's add that. So here we have added our switch statements which will return all the bullets based on the type. Let's go to our Okay, before moving on, let's create one more method, one more static factory method, which will actually return the bullet from the cache. So we will say public static bullet, and we'll call this get bullet from cache. And based on the bullet type, this will also return the bullet. But the difference here will be if bullet cache dot contains key and we have the type here, then only it will return from the bullet cache. Else what we will do is we will call our static factory method. We will say get bullet by type and pass the type here, and then we will add this type to this cache. So we will say type comma bullet, and the next time we are accessing the same, we are requesting the same type again, it will actually return from the cache. So we will say return bullet cache dot get type. So we are done coding our bullet factory. You saw what is the implementation for this factory. In this get bullet by type, we are actually returning the bullets based on the bullet type enumeration, and in this get bullet by from cache, we are actually checking in the cache whether this bullet is already present or not. Now let's go to our gun class and actually provide implementation for this. We will say protected bullet, and let's have an array of bullets, and along with the array I would like to have some capacity for this gun. So this gun has a array of bullets and a capacity. Also, it knows about what kind of bullet type it is holding. So we will say private final bullet type bullet type. Let's create a default constructor for this abstract class, which will be gun, and we'll say int capacity and bullet type will be bullet type. So let's set this. So we'll say this dot capacity is equal to capacity, and this dot bullet type is equal to type. After you are done with the constructor, let's add one more abstract method, which will say public abstract void shoot. Now every gun which will be extending this gun abstract class will provide its own implementation for shoot method. Let's create a method for loading the bullets into the class. So we will say public void load bullets, and in this method I just want to iterate over the capacity and assign this array with the bullet objects. So one with the bullet factory from the cache, and one only from the static factory, and we will see the differences how it actually behaves. So let me create one more method. We say public void load uncached bullets, and let me fill the implementation for this methods. Okay, so we have filled the implementation for this load bullets and load uncached bullets. The only difference between these two methods is this is actually asking the bullet from the cache, and this is actually directly asking the factory for the bullet. So there is no cache involved. Let's actually go to our shotgun class, and let's extend our gun. So I have already extended it. Let's create a default constructor which we will call shotgun, and we will pass capacity and bullet type. We will say super capacity and type. So we have passed this, and let's provide a implementation for this shoot method. So we will say public void shoot, and inside the shoot method body we will actually iterate over the uh, bullets array which we'll have from the gun class, and we'll try to print the object for each uh, object in that array. So we will say for int I is equal to 0 and I is less than this dot capacity I plus plus. What we will do is system.out.println. We will say this dot bullets of I dot to string, and this will help us visualize how this flyweight is trying to save our memory. So let's go to our hunter class and see this in action. But before actually seeing this in action, let's go over once more for all the classes we have created. So this is our bullet class, which will store the intrinsic state for our flyweight. Bullet factory will actually return the type of the bullet based on this bullet type. Bullet type is nothing but the enumeration, which has three kinds of bullets: pistol, shotgun, and sniper. Then we have a gun which has both intrinsic and extrinsic state, and we will try to use this flyweight design pattern to actually visualize the difference of memory when you actually use and don't use the flyweight design pattern idea. So let's go to our hunter class and give this gunner a gun and let him shoot some bullets. So now we are in the hunter class. We will just say some system.out.println, and we'll say shooting with cached bullets. And why I have written this I'll explain, but let's create a gun and we will name this gun shotgun, and let's give this a capacity of 8 and bullet type of bullet type dot shotgun bullet. So we have created our gun object. Let's load this shotgun with a lot of bullets, I mean 8 bullets. Now when you try to shoot the shotgun, when this hunter is trying to shoot from the shotgun, let's see what happens when we are actually loading bullets with the cache. So let's first run this program and see this in action. Okay, so we have our cool little text shooting with cached bullets, and you see every object in this array is having a reference to a same bullet object. Now let's actually go and create our gun with uncached bullets and see what's the difference. So shooting with uncached bullets, and let's create one more gun. We will say gun shotgun uncached, and this is equal to new shotgun. We will have the same capacity and same bullet type. Okay, so we have the same capacity and the same bullet type, but during the loading what we will say is shotgun dot load uncached bullets. But now since we are loading uncached bullets, it will not ask the factory to load the bullets from the cache. It will actually ask this bullet factory to actually load from this method. Let's go to our hunter class again, and we will say shotgun dot shoot. Okay, we are doing shotgun. Now let's run this program and see this in action. So for the first part, when you were using the cached version for the shotgun, you were actually referencing eight references for the single bullet, and every one of them was behaving and having the same values. But when you were actually using the uncached version for the bullets, what you see is you are using different objects for every bullet in the bullets array for the gun. But you know, right, all your bullet is storing the same information again and again, which is just a replica. So you don't actually need this different objects to store your immutable state. Now This is only with one shotgun, and it's consuming more 8 times more memory than the original shotgun. Let's say you have 100 guns, and how horrible will it be? Let's say your one bullet consumes 1 MB, and you are instantiating 100 shotguns, and which will lead to 800 MB extra memory. That is a hell lot of memory you are wasting. So always be sure to reuse your state if it's immutable. That helps a lot in saving memory, and that's the whole idea of flyweight design pattern. So let's come back again to our UML diagram. We have discussed this UML diagram in detail, and we have also seen a coding example. Let's go back to our definition and try to see whether we are able to understand how it is trying to save our memory or not. So it lets you fit more objects into RAM. Yes, because you are sharing common parts, which are the intrinsic states, which are immutable. So we have seen how we are sharing our intrinsic state. In our example, this bullet was our intrinsic state. So that's it guys, with the flyweight design pattern. And thanks for watching my video, and I will see you in the next one.